You're going to time me, right? Okay. Some of you may not know this, but one of Dwayne's first imaging projects was on a very ambitious way to implement, I guess it was called the no bald spot constraint. You know, like this. And he was able to, you know, he was able to greatly improve all the group photographs during his time at Cornell. So some kind of maximum likelihood matching, or I forget what it was. Right. So I see a lot of young people out there, and I'm reminded that at one point I was young, and at that time I remember always wanting to work at the cutting edge, at the forefront, at only the most exciting, most recent things. And that's generally a good principle, but let me show you a graph that made me a little bit concerned. So this is this is showing the instances of the phrase phase retrieval in abstracts on the archive in the last 17 years. And oh, is there one of yes, right here. Right, so it looks like something really important happened right around 2011. Okay? And so if I saw this, or if I noticed this going on as a young person, I would think that, well, I only want to read these papers, because obviously something super important happened, and I don't want to mess with all that old stuff, because this is obviously much better. Okay, so let me just show you a random couple sentences from one of those papers. I think this may even have been the one that started the revolution. I forget the exact authors on this. But anyway, these people, they do understand that the most important application of phase retrieval is X-ray crystallography. We would not have a protein data bank if phase retrieval didn't work for crystals. Okay? That's a big deal. But then if you keep reading, this is the stuff highlighted in red, you start worrying whether maybe these authors even know what X-ray crystallography is, right? I mean, they're saying something like, well, it's evolved, but it's developed techniques to recover Bragg peaks from, well, look, if you don't see Bragg peaks in the data, you don't even have a crystal, okay? I think, okay, to be fair, I mean, I wouldn't show this view graph in audience of these applied mathematicians who do this work. You know, don't get me wrong, these are good people. They could use a little educating, and maybe I'll give talks like this one, maybe certainly without this slide. But when you see this, it gives pause to whether, you know, how seriously should you take this wave of new research if they don't even know the fundamentals. Okay. All right, so here's the plan. My outline. I'm going to impress upon you that there's this period prior to this event where there were a lot of really important key ideas, and we should not forget about those. So I'm going to give a breakneck review of those important ideas, and I'm not going to try to be comprehensive in a historical sense in terms of dates, people, and all that. Although, you know, you should be aware there's some really, everybody should know these individuals, the key players in the development of crystallographic phase retrieval. Unfortunately, only one of these is still with us. That's James Phenom. But okay, that's the first part. And then I will present sort of my view of where we are now the state of the art of crystallographic phase retrieval. And finally, this last item is a recent effort to try to bring this powerhouse called applied mathematicians, these people who are working on stuff which doesn't actually have the simplest way to say this is none of the research in this last 7 years signaled by that rise in publications, none of that research has led to any algorithm that any scientist would want to use. Okay, and so this last thing I'm talking is a project where what we want to do is bring these people into this useful research area, crystallographic phase retrieval, and everybody will be happy. I think scientists will definitely profit from that, but also the mathematicians will as well. So let's start in with this review. Okay, here we go. So I guess the first big thing in phase retrieval for crystals was realizing that it's a problem that could be solved. Okay, I mean, think about it. You don't measure the phases. What can I do, right? That's your first reaction. But people understood right early on that if the thing you're trying to reconstruct is just where are a bunch of atoms, then it's actually quite reasonable to expect that it can be done. Now, this cartoon here shows what's involved with the measurement of an intensity. Okay, you do an integral of the density, these atoms, over a unit cell, and there's this discrete index. Here's the case h equals 3, so it's just where the sine wave happens to line up with those atoms, and you get a signal like this would not contribute anything. It's near a node. This would give a negative contribution, another negative contribution, and look, if you just go from 3 to 4, you get a very different piece of information, right? Now this one has gone from negative to positive in its contribution, and this one has gone to a very small, what I'm saying is you pick a random H and you get a independent piece of information. Those atoms are always the same places. You're just sampling different. You're just taking different measurements on the same thing, simple thing. Okay, let's get a little more quantitative. Suppose we're in 3D now. You measure a range of these intensities. There's 3 indices. Let's say they go between minus m and plus m. Okay, so what does that mean in an abstract way? It means you've, in principle, have a representation that holds on a grid. I'm just showing a 2D grid. Think of a 3D grid, which measures 2m plus 1 on each side, right? The range of these variables. So what it means is that at this level of Fourier information, you can hope to localize atoms in one of these bins. Okay, and then you can ask, about the information requirement to locate those atoms, and if you have n of them, it comes out like this. Okay, start with this. Like if you have n atoms, they have 3 coordinates each, and the number of bits of information to locate the bin is just log 2 of 2m, or 2m plus 1. So this represents how much information is required to define your atom configuration. Meanwhile, right, you've got all of these intensities, m cubed. No, I'm sorry, 2m cubed, right? That's how many there are. Maybe I should divide that by 2. Yeah. Friedel symmetry divided by 2. 2m cubed numbers that I measure, right? How many bits of information in those numbers? Well, it depends on my signal-to-noise ratio. There's always noise. But basically, this is, I guess, up to that factor of 2, I just realized. This is the estimate of how many bits of data you're acquiring in your experiment. And you can see these scale very differently. So forgetting about the log factors, it just says, you know, if you make this m big enough, so m cubed is quite a bit larger than n, the number of atoms, you're in great shape. It says that, you know, not only do you have enough information to determine the positions of those n atoms, you have safeguarded yourself against all kinds of bad things like noise, right? All those measurements come with some noise. So having the data strongly overdetermine the structure is a good thing. So, you know, this is what happened really early on, and I think it quieted all those critics that said, look, you're not measuring phases, so fundamentally you can't do anything. No, it's not true. We have a lot of knowledge about the thing we're trying to reconstruct, like there's where are all these n atoms, and then you can do it. All right. Now, here's another important development. This has to do with what are called phase invariants. So let's look at the 3D situation where the HKL indices form a vector Q, and now you're integrating density over a 3D unit cell, right? And I'm calling these Fourier coefficients rho hat. Okay, when you see a hat, it's a Fourier. No, it's a complex number. And the thing is, we're talking about crystals, and it's interesting to ask what happens when I just translate the stuff in the unit cell by some amount. Remember, the crystal unit cell is periodic. When I move the molecule, it'll wrap back around on the other side. So I can apply translations. Well, when I apply a translation to this row here, what happens to this rho hat? Well, very simple. Its phase rotates. And so, if you think about it, the absolute phase of one of these rho hats doesn't mean a damn thing, right? Because it's sort of arbitrary where I decide to put the origin, where I decide to, center my molecule in my unit cell. That doesn't mean anything. But there are things that do mean something, and that's listed here. So we're looking at what happens when you do a translation, right? This is not good. This is not useful, right? Its phase will just rotate by an amount proportional to this translation. But if you take the product of two of these rows, one with a Q and one with the opposite, while one rotates this way, the other one will rotate exactly the opposite way, and they cancel. And you do get something which is invariant under translations. But I already knew that. That's the intensity, right? The intensity is not only a real number, it's a positive real number. So its phase is fixed for all time. Its phase is always 0. But you can go on. You can say, okay, let's take a product of 3 of these where the Q's are set up just like this one, so they add up to 0. Right? Again, under translation, each of those rho hats rotates some amount, but combined, their product doesn't rotate at all. It's an invariant. As soon as you realize that, you ask, if this is an invariant, maybe it can tell me something interesting. So let's look at the values of these invariants. So, this one was trivial, right? The phase of this is 0. Phase angle is 0. But what about these guys? Okay, so let's do this experiment. We're going to take the product of these 3 complex numbers, where Q1 plus Q2 plus Q3 is 0. Okay, I can think of that as a product of their magnitudes. I know that, right? That's the measurement. What I don't know is this combination of phases. Okay, and let's call the complex number F plus IG. Okay, so suppose I have 3 atoms. what I can do is I just do an experiment, right? Compute for some choice of Q1 and Q2 and Q3 that add up to 0. Compute that and plot f plus ig. And I'm going to do, that's the only movie I have. Pretty cool, right? Yeah. Yeah. And so I'm not going to assume any chemistry knowledge, like where are these atoms? Let's just imagine they could be anywhere. All right? They can even be on top of each other. Who cares? And I'm going to plot this f plus ig for all of those random arrangements. This is what I get. So right away you notice something kind of interesting. There is a pretty limited range of complex numbers that you get. Right? You don't get, it never comes out here or there or there. And the other useful thing is there's lots of information there, especially if the magnitude, that's the product here, if the magnitude is large. If magnitude is large, it means I have to be far from the origin, right? The only way I can be far from the origin and still be in the allowed region is if I'm right there. So, you know, if I'm lucky and I find a combination of 3 of these row hats, or, you know, 4 magnitude measurements, such that their product is exceptionally large, I know a lot about this combination of phase angles. I know it's close to 0. Okay? If the product isn't small, then I don't have that much information. But think of it this way. You know, you do a lot of measurements. There are a lot of triplet combinations that could work. And that was the strategy of those early days of crystallography. It's like, we should expect to be lucky some fraction of the time and find combinations that have large magnitudes. And then, you know, and then I know things like, if I say I knew these two, then I would know phi 3. They're strongly correlated in some instances. And the idea was then to solve this big puzzle, right? Combinations of phases that satisfy these loose or sometimes very tight constraints. Now, you know, if you want to implement this, there's issues. That's the distribution when you had 3 atoms. If you have 5 atoms, you know, it's not as great. You know, in order to know a lot about the phase combination, the triplet phase combination, you know, the magnitude, product of magnitudes has to be pretty large. And even then, it doesn't really restrict the range too much. And even, you know, as you go up in number of atoms, it gets worse. But people were not deterred, right? They were tough back then. They're not going to give up. And I think it was always with the understanding that there are just so many triplets. And if each triplet only gives me a small bias in aggregate, getting all of those phase triplets to correctly reflect even a small amount of bias, that could be enough. And that turned out to be the basis of the early phasing algorithms. They cooked up things like objective functions, right? Cost functions, which try to impose these biases on phase triplets. And what was nice about this whole subject area was in the model, which is not that crazy, for uniformly randomly distributed atoms, you can work out these distributions analytically, right? You don't even need computers, you just need pencil and paper. This whole era of phase retrieval was marked by very little use of computers, and it's pretty impressive. All right, now, at some point, it turned from the question of like, okay, we know in principle one can find phases, and we know they are correlated. It turned from that to design an algorithm to find those combinations of phases that have all those good properties. And the way things turned out is algorithms that were fundamentally iterative were invented, okay? And so this is, you could think of this as like the first time iterative algorithms in image processing showed up. And it's a very interesting story. And we'll start with this thing called Sayre's tangent formula. Okay, and you know, I think many of the people here will not know about this, whereas you probably do know about this more recent approach in this spirit, where you design an iterative scheme to find combinations of phases that have these good properties. But you know, it's worth going back to how this one worked out. So let's think about a crystal again. And so this one works in an idealization, which is actually not so bad for lots of materials, where all the atoms are the same. Okay? Let's say you're working mostly with biomolecules. Most things are atomic number right around carbon, right? Carbon, oxygen, nitrogen, they're roughly identical. Okay? So then you have this cool property that was that was exploited by Veit Elser. It says that when you square such a density, you don't change the Fourier phases. That's a pretty big deal. Here's a picture. It shows a density like 3 atoms. You square it, you get the same 3 atoms, but their contrast is sharper. And I can think of that process of squaring equivalently as taking the sharper atoms, the square density, and blurring them with a convolving them with some symmetric blurring point spread function G. Okay. Now, what is that? You do some math. You think about Fourier transforms. So convolution, right, in real space is a product in Fourier space. Okay, we know this. And if you think about the phases of these 3 factors, it just says the phase of this equals the sum of the phases of these 2. Okay. Meanwhile, the phase of G, the symmetric blurring function, think of it like a Gaussian, phase is 0. So it says the phase of rho, of Fourier transform, rho hat, is the same as the phase of when you square it. That's a kind of quirky fact. Now, Veit Elser's genius was to turn that into a useful equation for phases, and here's how that works. Right? I can think of it. I can use that same convolution theorem again and say the Fourier transform of the squared thing is the convolution of the Fourier transforms. Right? That's true. So I can write now an identity that says, since the phase of rho hat is the same as the phase of rho squared hat, and rho squared hat is that, I now have an equation relating phases, right? This has phases, and this is some weird combination of phases that you get from this convolution operation. And this is some nonlinear equation involving just phases, and it has the magnitudes in there too, but those are known. Okay? Why is it called the tangent formula? Exercise for the young people up there. If you write this out in terms of real and imaginary, the complex numbers in terms of real and imaginary parts with sines and cosines, and you just do a couple lines of algebra, you'll get some tangents. Okay? It's a very mysterious nonlinear equation involving a bunch of phases. Okay, right. And so the beauty of that is you have a kind of very non-trivial, non-linear transfer. You can think of it as suppose you just define this transformation, some abstract transformation, which happens to depend on these parameters. Okay. It has this great property that if you applied that transformation to the correct phases, the thing doesn't change, right? This is a transformation with magic property that if you plug in the correct phases, it's a fixed point. And that was the basis of the algorithm. David Sayer, first came up with this, and they said, okay, let's turn it into an algorithm. Here's the algorithm. You say, okay, let's we don't have any prior information phases. Just pick some random ones, some guesses, and then you just iterate this thing. Right? New phases, stick them into the formula, get out some new phases, keep going, and then you cross your fingers and hope at some point they stop changing, right? And if that happens, it's a good sign. It says those phases are now consistent with a model where all the atoms are as you expect them to be, identical carbon atoms, something like that. And so this was the basis of the first iterative algorithm for phasing in crystals. And believe it or not, there are modern, state-of-the-art phase retrieval algorithms used by crystallographers that have this as a subroutine in them. Right, yeah, I forgot. So you get the phases, but then, to get the atom positions, you attach those phases to the magnitudes, and then you have the correct complex amplitudes, then you can get the atom positions that way. Okay. Now, move ahead a couple decades. In the meantime, the fast Fourier transform has been invented, and all kinds of new and more direct ways are available for imposing prior constraints on your density. Okay? People are sometimes dismissive of all this Sayer stuff, tangent formula, because they don't understand there was a time without the FFT. In those early times, people couldn't just easily go from real space to Fourier space and do whatever needed to be done in one or the other. So they were just working in Fourier space. They were always just working with phases, and now But so now along comes Jim Feenup, right? He's not even a crystallographer. He's trying to find Russian satellites or something. I don't know. It's all classified. But anyway, it's a similar. But I'm going to frame it as a similar kind of thing. So think about it. Think about an object. So now we don't even require that there's atoms. It's just some blob, right? But I can think of that blob as being in a unit cell, right? Some virus or something, and it's kind of weird. What I'm going to require is that this object occupies. So we're just going to make 2D pictures for now. Occupy just one quadrant. So it's in a very generous unit cell. What's nice is that I can now insist call it a computational grid. I can insist this is periodic, right? Just like it was a crystal, because when I do that, I don't make an error in the following sense, right? Think about what the autocorrelation of this object is when computed in this box. Right? If the box is big enough, so when I do the autocorrelation, there's no wraparound of the object on itself. So the autocorrelation computed in that periodic box is identical to the autocorrelation of an object isolated in infinite space. Okay? And that is the experimental condition that applies in coherent diffraction experiments, or whatever Jim Feenup was doing. Who knows? Okay? So that's great. The phase retrieval problem has been turned into something a bit different now. It says we have a bunch of density, and we have magnitude measurements of the Fourier magnitude measurements of that density. And the trick now is to figure out phase combinations that move all of that density into one quadrant. Okay? I'm not trying to make atoms. I'm just trying to shove all the density into this one quadrant, because I know that should be possible. I guess that assumes I have some estimate about how big this thing is. Let's say somebody tells me how big the satellite is or whatever, And then I just generously put it in a big enough box, and I'm good to go. Now, let's get back to this business of whether it's whether I have sufficient data. Now, let's think about this. If I have this, if I represent this in a computational box of this size, 2n by 2n, when the object is n by n, right? It means I have available Fourier magnitudes appropriate for a box of this size, 2n by 2n. That's 4n squared intensities. Now remember, there's also, for a real valued Russian satellite, I guess, there's a Friedel symmetry, so there's half that many intensities. Okay, we have 2n squared. Okay, we have that many measurements, but we're only trying to reconstruct n squared pixels, right? So it's good, right? We're over constrained. Now, this also led to an iterative algorithm that works like that. The idea now, because we have the FFT, let's iterate rho as opposed to just phi. Okay, and we use this idea that we can make these apply these transformations to any rho, so that the transformed rho satisfies some constraint. So here's one obvious transformation, which says, you give me any rho, okay, and I'm going to make sure that the new rho I get has the correct measured Fourier magnitudes. And so it's simple. Here, these are the measured ones. So I just take the phases from the input, attach those to the magnitudes, and now the result is something, who knows, that at least has the correct Fourier magnitudes. And the beauty of that is there's a similar transformation, or you can think of it a similar way, that does the following. It says, my density here should only occupy that upper quadrant, right? It should be 0 everywhere else. I can also restore that constraint very simply. I just zero out all those other pixels. So I have these two elementary transformations called projections, and the idea is to build an iterative algorithm based on these two. Okay, and what I know going in is that if I stumbled upon the correct rho, the beauty is that neither of these operations will change it, right? The correct rho, by definition, has the correct magnitudes, and I won't be changing it with that. And it's also, in the correct place in my computational cell. So I design an algorithm which keeps rho fixed, the correct rho fixed by both of these transformations. And where's all the phasing going on? Well, it's actually this operation, right? This operation keeps the old phases, doesn't change them, but it's this. It's called a support projection, forcing all those the pixels outside of the support to 0. Will change the phases. Okay. Okay. These are the building blocks. The algorithm, obvious first guess might be you apply this transformation, that gives the correct magnitudes, and then you follow it by that. Now it has the correct support. That'll probably mess up magnitudes, and so you have to repeat this. Unfortunately, that doesn't work. It just falls flat. If you stop there, that would be the saddest thing, because you're so close. If you just change the formula a little bit, it works like magic. Okay? I mean, that's what's so amazing, that defining these operations was kind of big deal, and then just the next step is combining them in the right way. So this is Jim Phenop's magic formula, the hybrid input-output map. It's mysterious how he arrived at that. The main thing is, it works like gangbusters. It's amazing. I can give a whole lecture on just this thing. Okay. So that's the first part of this presentation, the main part. So just make sure we understand the main points. First was understanding phase retrieval could be solved if we know enough prior information, like that there's atoms. And it's a good problem in being overdetermined, and so you can manage noise. There are lots of constraints on the phases. Right? The phases, those constraints might come from the fact that you have atoms, or that we know the size of the object. We can embed it in a computational box, as in coherent diffraction imaging. And finally, there's this common theme that if you set something up, an iterative scheme, which has a property that stops changing when everything is consistent, when you hit on the right density, this fixed point idea, you have the basis of a really, of a practical algorithm. Okay, so we're getting to what I call the state of the art. The state of the art, I would say, represents a framework where you do all your work with these projections, okay? Technically, it means define operations that minimally modify your current thing, your input, so it satisfies a particular constraint. We saw two examples. So they're called constraint projections. And what you have to bear in mind is that you can write this either this way as acting on the density in real space, or no problem, just think of it acting on its Fourier transform. It doesn't matter. Rho and rho hat are equivalent representations of the same thing. They're just related by an FFT. Okay? And yeah, so there's the one important instance of one of these projections. You restore the correct magnitudes. Now, there's all kinds of crazy stuff you can do with the other one, right? So we saw this one already. You have an input row. You know it should only occupy the upper quadrant, so you zero out all of these. This is what you would use in an experiment where you're determining the structure of an isolated object, as in CDI. But look, kind of trivial change where you say, okay, now I'm working with crystal data. This is a periodic unit cell. Where are the atoms? Well, I don't know, but I know this great property that atoms are pretty compact. Most of the unit cell is empty. So if I know about how many atoms there are, if I know my resolution, I know how many pixels are, then I know how many of these are allowed to be non-zero, right? Because I'm dealing with a certain known number of atoms. How do I do this projection? It's very simple. Remember, the key word is minimally modify. So how do I minimally modify this so I only have a certain known area of density? Well, I pick the largest ones, and the others I set to 0. So it involves just sorting the values and keeping the certain range of largest value. So it's very easy to implement. Okay. Now, there's also been a kind of an advance in hybrid input-output thing, right? Here I'm calling the projections P2 and P1 because it doesn't matter, right? It could be Fourier magnitude, constrained, a support, whatever. It always has this structure. Now, I put this relaxation parameter, beta, and the algorithm now has a slightly different name. It's called relaxed reflect. This is trying to indicate that it's a big deal about, having freedom to choose this is kind of a big deal. It's a conceptual thing. Now, here's a cartoon to give you an idea of what's going on. Okay, this is not atoms or anything like that anymore. It's really simple. All the action is happening in a 2D space, right? Rho is a two-component thing. And it's a toy problem. One constraint set are these 5 dots. So P1, what it does is just takes you, wherever you are, it projects you to the nearest blue dot. And The green line is the other constraint set, right? So the projection says, wherever you are, take me to the nearest point on the green line. Okay, and there's an intersection of the blue set and the green set, and that's a solution. Right? That's where you're unchanged by either projection. Now, what's interesting and what I think a lot of people find mysterious about this algorithm is when you run these algorithms, you don't just run to this point. You run to any of these points represented by the red dashed line. All of those are fixed points, and all of them refer to this solution. Okay, so there's more places to end up at than you might successfully end up at than you might naively think. Now, what are all these streamlines? Well, this is where this thing comes in. To understand this RRR more fundamentally, the idea is take the limit where this beta goes to 0. When beta goes to 0, you can think of this as being like a time step, right? It's saying, it's like this is a velocity and this is a position, and you're moving the position by this is a vector velocity, right? So you take this, I call it the flow limit, and you have this system of differential equations, and this just shows the flow. And what's great about this is you can just check right here that it's always going to succeed. It doesn't matter where you are. Let's say you're here, you flow, flow, flow. Here, you actually flow along the green line, and you go there. On the other hand, if I start here, God, I'm shaking too much coffee. So I flow, 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 and then I flow up here, and I'm at the red line. I'm still at a solution. There's no place to mess up. How could it mess up? Well, you could end up maybe going in a limit cycle, right? Okay, like I said, I can give a huge lecture on just this thing. So we're at this point where I'm going to now try to make crystallographic phase retrieval sexy again, right? So young people and applied mathematicians will start working on it rather than the kind of silly problem that they have been. Okay. And so the idea was to set up challenges, right? What better way to establish a winner or something that will improve the state of the art than setting up a bunch of benchmarks. So these are designed to be crystal-like, so that means crystallographers will benefit from the product of this research. The contrast is atomic, and as already illustrated, simple way to impose that is through support area. Only such and such a fraction of the unit cell may have density. And these have been very carefully designed to have an index of hardness, because it's not just, I don't think it's enough to just show that your algorithm can solve this one, whereas this other algorithm can't. You want to know things like, how does one algorithm behave over a range of hardness cases with respect to some other algorithm. You want to know behaviors. And there's noise. And if you're interested, so this is a publication, and there's you can download the benchmarks, and there's even an RRR solver that you can play with there. Okay. So this is what these instances look like. They're 2D. The reason for it doesn't matter too much, but 2D is nice. You can make pictures and see what the algorithm's doing in real time. They are all on 128 by 128 pixels, and they differ in the number of atoms. The more atoms, the harder, right? Because as you put more atoms in, you have less power in the support constraint. There's less pixels you can set to 0, right? Because you need to have room for those atoms. So that's roughly how things go. The more atoms, the harder. And just to make it, I put in two kinds of atoms. There are big atoms and little atoms. Here's what the data looks like. There are grids of half the size, right, because there is Friedel symmetry, of photon counts, okay? And that's the only origin, the only source of noise. The Fourier magnitudes are measured in a photon counting sense, right? So these are subject to Poisson statistics. Notice there's a 0 up here. Crystallographers will be happy because nobody measures the 0, 0, 0 intensity, right? X-ray beam goes through a hole in your detector. But that's okay. Phase retrieval works even when some fraction of the intensities are missing. So this turns out to be a new thing. I had some email exchanges with George Sheldrick, and it's just like asking him. He's the international acknowledged expert in crystallographic phase retrieval. We were, like, how do you know whether this structure is going to be hard? Like, how do you know if this one's going to be a challenge for your software, which, by the way, is called ShellX. And here's what came out: that what you really care about is this thing I call the mean multiplicity of interatomic vectors. And here's a picture showing what's going on here. Say you have a bunch of atoms, okay? And here's an interatomic vector. Okay? Fourier magnitudes tell you the autocorrelation of this, right? It's equivalent. The Fourier magnitude information is equivalent to the autocorrelation of this distribution. Now, if we imagine this thing is not in a crystal, but in isolated, infinite space, I would compute the non-crystal autocorrelation. This is a picture of that. Right? So this autocorrelation vector corresponds to this atom pair. Now, what changes when it's a crystal? Well, everything wraps around. Here's the unit cell. Okay, so whereas in the non-crystalline case, the autocorrelation vectors thin out, right, they are more or less uniform density in the crystal case. And I think that pretty much should convince anyone the crystal problem is much harder than the non-crystal problem. Because look, if you go way out, the idea is to start way out here, where these are also called Patterson. This is called a Patterson map, right? Where a Patterson map is sparse. So there is some pair of atoms represented by this vector. So you can just put them there and there. And then the idea is to tick off autocorrelation vectors on the periphery here where they're sparse by putting in a new atom and keeping all the new autocorrelations you're generating that way consistent with this picture. And as you're adding atoms, you're removing things from here, and you can do it in such a way that it stays thin all the time. There's always a place where it's easy. But you can't do that in the crystal, right? Where do you even start? And so what this measures is how many of these autocorrelation vectors are there per pixel, right? The density of them. The denser this is, the harder. Here's a more formal definition. So the number of atom pairs scales as n squared, right? So that's how many autocorrelation vectors there are. And to compute the density, we have to, put them in this grid that's defined by my resolution, right? The atom size. And so how do you get an estimate of that? So this gives a density. How do you get that? Well, you want to use a way of estimating that refers directly to experimental data. You want to have something as directly related to your measurement as possible. Well, in the data sets, especially for large structures, you have this thing called the Wilson B factor. It's describing the systematic decay or envelope of decay of intensities. It's also called the Debye-Waller factor. And so if you just sum this over all the Bragg vectors, you get a number. It's just a dimensionless number. And it's an estimate of how many Bragg peaks or how many voxels you have. And so this is the state of the art, okay? And there's a lot going on in this graph, but I think it's got an important message. First of all, here's the hardness index. Right? We're going from a density of autocorrelation vectors, which is very, very low, this is easy, to increasingly denser, vectors piling on top of each other. And that's getting harder. There's these 3 lines on a log plot. So already you go, oh dear, this is bad. Okay? The algorithms are taking exponentially many more iterations to solve a structure as mu is increasing linearly. Okay, so you would say this is not good news, but the point is this is the best we have, and the structures you find in the protein data bank owe their existence to the fact that we've been able to get up to this line. This is as far as. So I did a survey of crystallographic phase retrieval where they were able to use an atomicity constraint. You can't do that when things get really big, right? Because the atoms are more fundamentally blurred out. But you can get up to this point of mu about 12. Okay, and now there's these 3 curves. Now, so there's also a possibility that at a given mu, some instances might be harder than others because it's possible that the distribution of intensities has outlier characteristics. Okay, so this is a sort of another level of refined estimation of hardness. Imagine you have, for whatever reason, some intensities are unusually large. Okay. That turns out to have benefits in terms of a lot of phasing algorithms that rely on combinations that have a lot of measurements where the intensities are unusually large. So I try to set up in the data in the benchmarks 3 families. So there's an average case or middle hardness is where you don't try to skew the distribution of intensities anyway. You just sort of generate random structures. But then you can skew the distribution of intensities in a positive way, make them easier, or make them harder. This is systematic. And what's interesting is RRR. The RR points track different lines. So that's what I'd like, I would think a positive outcome of this is these applied mathematicians will see this and look at this as a challenge. First of all, can we even solve one of these? Okay, it turns out there is a class of algorithms they've developed which apply to mu much less than 1. So they can work right in here. I'd like to see them solve some of these structures, mu out here. And not only that, I want to have them make a plot and see a slope. And if they can improve on these slopes, more power to them. So that's the idea, and I hope it works out. And I have to acknowledge my collaborators on this project. You heard Tien yesterday. He does other things besides insanely noisy crystallographic intensity reconstructions. And so this is the most positive outcome so far. This guy's an applied mathematician. He didn't know about crystal. He doesn't know what a space group is. He doesn't know any of that stuff. But he got excited about this project enough to become a co-author. And there was a development that happened just during my epic journey from Ithaca to Singapore that I want to share with you. So can I do a bonus slide? Okay. So, we told, this is thanks to Tien, who can turn my code into MATLAB code. And it turns out these mathematicians just can do MATLAB. So, so we gave Tamir a MATLAB version of RRR, and we got all these like crazy emails like, I can't believe how great this thing is. Look. Oh, yeah, I first have to tell you, okay. So it's too much to ask them to understand crystallography right off the bat. So this is the problem that all these mathematicians are solving. This is the problem that nobody cares about except them, okay? Right? No, it's a reasonable problem, but it's limited. Okay, here you're trying to find this vector of complex numbers. There's n complex numbers, and how do you find out about this vector? Well, you take its dot product with some known complex vectors called sensing vectors. Okay, this dot product is a complex number. You strip it of its phase. I just tell you the magnitude. That's why it's phaseless. Okay, now you have these are real numbers, these measurements, and you're trying to reconstruct complex numbers. So you're trying to reconstruct, too many of these. So how many of these do you need? You need at least twice as many of these sensing vectors, right? Because of the mismatch. So it doesn't even apply to Fourier measurements. Fourier measurements, there's only n of these. Okay, that's why we need prior information. But anyway, let's do their problem. In fact, I found out that's the key to making any progress. You can't just say, look, this is stupid, do our problem. No, you have to say, okay, I'll do your problem, okay? And we'll see what happens. And that turned out to work with Tamir, because as soon as Tien gave him the MATLAB code for RRR to do this problem, that's when he got excited, because he sent me these email attachments. Look at this. Here we're reconstructing complex vectors of length 50, right? And I would argue it's already a well-posed problem when the ratio m to m is just epsilon greater than 2, okay? And this is the success rate, like how this is, you give it a different initial point number of trials, and you ask, how often does it get the answer, okay? Well, these three right here are state-of-the-art from the applied math community. Right? This is called phase lift. This one's called truncated Vertinger flow. I have no idea what that is. And then this is non-convex phase cut. Again, I have no idea. And the reason we were able to do this was because this brand of research, they always upload their MATLAB code. So it's a question of running their MATLAB code. And so that's how they do. This is RRR, okay? You might say, well, the only reason RRR is doing so much better in terms of success rate is because it's like working harder. Okay, but that's not true either. Here's a little table. It says how much time it spends finding these solutions. Right? Here's the hardest one, 3. For some reason, okay, there was no point doing these down here because it would just take too long. That's why I started at 3. Okay, so RRR takes a lot less. In fact, this one just gave up. All right. Well, I hope you're inspired to maybe try your hand at some of these phase retrieval benchmarks, and I'll take questions.
What kind of projections were used for this?
Yeah, so it turns out for RRR is a very nice way to do it. One projection says, I guess I should go back. Okay. So the search variable, it's always, the first question is, what space are you searching in, right? Turns out the smart space to search in is these dot products, these complex numbers, before you take the magnitude. Let's call this y. And you have actually not just one y vector, you have m y vectors. Okay? No, wait, I'm sorry, I'm sorry. It's... No. There is. I don't have enough notation here to make it clear. I can explain that later. But just to answer your question in just a couple statements. One of the constraints projects to a linear subspace. So you go from a large linear space to a linear subspace. And it's a linear subspace that's spanned by these AIs. Okay, these AIs are, think of them as a smaller number of vectors in a space of higher dimension. So they span a lower dimensional subspace. So one projection projects onto their linear span. So that's a pretty easy projection. The other projection just projects to vectors or y's which have the correct magnitudes. It's same as the Fourier magnitude projection. So those are pretty easy to implement. In fact, what's interesting is TN's MATLAB code for doing this is as long as the wrapper code for the other the other applications. You just have a bunch of stuff like this vector. Here's the data. Here's the loop. Here's a criterion for stopping, and then in the middle is call this library function, okay, from this package, which is thousands of lines of code, okay. So what's interesting is TN's MATLAB code, which has it doesn't use any library functions at all. It's just straight MATLAB. That thing is as long as these other things, which rely on giant packages. Yeah, right. And in all fairness, that's how these mathematicians give some argument why it might apply. What they do is they say, think of an experiment where you put behind the object a phase mask of your choosing that you design. Okay, so then if you pick 3 different phase masks, it's like you're taking 3 Fourier-type measurements, but with this phase scrambling. And now I've increased my data by a factor of 3, and it should work. Okay. The problem is that you can't do this for crystals. Like you can't put a phase mask in a unit cell. Oh, yeah. So that was made crystal clear in the statement of the benchmark problems. Because there's noise, you have to be clear on that. And so for each instance, which involves a number of atoms, you are required to have density on only certain fraction of pixels. And to establish that you got the right answer, you compute the total power, the sum of the squares of the density on those on the support. And if that total power is above 95% of some normalized total power, you're good. So it's a very clean success criterion.
Any further questions?
Yeah, look, when you set beta equals to 1, it's hybrid input-output. Or everybody calls it something else. Convex math people call it Douglas Ratchford. You know, there's all kinds of names. And so in that class, where they just differ by this one parameter, beta, you can make a strong case that the limit beta goes to 0 is optimal, the flow limit. And I have a paper on a phase retrieval problem where contrast is bits, which I call bit retrieval, which you can read and you can see the argument there.
I'm going to insert a question.
Oh.
So what you showed was that the isolated object case, it's kind of like the crystal case. It means all the densities one corner.
Right.
So on your easy hard medium plot,
Yeah.
where would
Oh, right.
that thing be, that problem?
Oh, I think, yeah, it doesn't even go exponentially, like goes along like that, yeah. Yeah, yeah. CDI, in terms of phase retrieval hardness, is just really, it's just not even, it's not exponential, it doesn't have an exponential growth in hardness, yeah.
Okay, think right again.
Okay.